Thank you. I'm delighted to be here. You know, for me, this is a little bit of deja vu. It was roughly 40 years ago that I got switched from being a programming language and compiler person to first doing work in CAD and then in computer architecture, stimulated by the DARPA VLSI program. It changed my life. It changed Silicon Valley. It changed the world. And I think that's what the US investment in research really does for our country. It keeps us in the lead and keeps us thinking about it. Well, we're in an interesting time. We face a new set of challenges, which I want to talk about. The end of Moore's Law, it's been talked about a lot. For me, this is also the end of a simple path to build faster general-purpose machines. But it's also what creates a new opportunity, a resurgence that we can think about new ways to build computers, new ways to think about semiconductor technology. So what I'm going to talk about is what's happened and why it happened, something about what some of the opportunities are, and the research possibilities I see coming out of this. 40 years of absolutely stunning progress when you think about it. If you think about the aggregate composed advantage, the amount of performance we've gained in terms of computing, it's roughly 10 to the 6th in terms of microprocessor performance. 1 million times faster. That's an incredible achievement. And it happened through a variety of things. Remember the first Intel microprocessors, 4 bits wide, up to today, 64 bits and wider. It happened with instruction-level parallelism, going from machines which took many cycles to complete an instruction to processors which did more than one instruction per cycle. So lots of things happened, and then most recently in the last 10 or 15 years, the rise of multi-core, putting multiple cores on a single chip to try to get more parallelism out of the processor. All those things contributed to that change. And of course, clock rates also got faster. When we look at clock rates, it's important to remember that 2 things happened. The basic transistors got faster, and we got a lot more. We used the more transistors to do things like pipelining and multiple issue that could speed up the pipeline and make the clock run faster than it would have if we'd relied just on faster transistors. All that was made possible by integrated circuit technology. Take away integrated circuit technology, and the computer industry is still these slow, bulky, big machines. So that's really critical to understand that. Moore's Law, the growth in transistor count, and as my good friend Gordon Moore said recently, no exponential goes forever. Remember that, no exponential goes forever. But also, equally important, and much less frequently mentioned, the importance of Dennard scaling, the ability to drive down the energy per computation. And I'll come back to both of those points. But 3 things are converging at the same time. First of all, technology, right? End of Dennard scaling, slowdown in Moore's Law, transistors cost, energy and power become the primary design criteria for everybody. Architectural changes as well. The end of the instruction-level parallelism road, challenges in doing multi-core, Amdahl's law, which we all thought maybe was eliminated. The problem with theorems is that they don't get eliminated. They just sit there, and unless you change underlying parameters or assumptions, they stay. And then a shift in application focus. This is equally important, sometimes overlooked, that we're shifting away from a focus on big machines that either sit on a desktop or sit in a computer room, at least in some instances, to things that you carry in your pocket, to IoT, a very different world than the one we're used to. So look what's happened. This is a great slide because it really shows what's happened in processor performance. We had this early period where we were getting about 25% a year. Then the invention of RISC and instruction-level parallelism leads us through this period. We get 52% growth in performance per year, a phenomenal achievement. If we got that on cars, we'd all be driving these little cars that would pack up in our suitcase. We'd get 300 miles to the gallon and would cost $50. Then a period where things began to slow down. We moved from ILP to multi-core. More slowdown the last few years, dramatic changes, limited both by power concerns as well as by architectural ideas and what they pay off. Of course, we can see this in DRAMs quite acutely, 50% per year in this region, 40% per year here, most recently 10% per year. Now, DRAMs, as we all know, are particularly unusual technology, and this exaggerates the effects. But even if you look at Intel microprocessors, for example, you can begin to see the Moore's law deviations begin to really creep in. And look here in roughly the last 5 or 10 years, you see that gap continue to grow. By the time we get out here today, we're 10x transistor count off what we would have been if we'd sticked on a straight Moore's law curve. So we're beginning to see the effect of that dramatically. But we also see the effect of the end of Dennard scaling. The wonderful thing about Dennard scaling, when you think about it, I mean, the simple way to say what Dennard's observation was, is that power, because of scaling of capacitance and voltage, power per square millimeter was a constant. If power per square millimeter is a constant, when I go from one generation to the next, it basically says the amount of computation I can do, the amount of transistors I can have for the same power budget is dropping. That said, cost energy per computation was actually going down. What's happened with the end of Dennard scaling is that power per millimeter is no longer a constant. It's going up, actually, or not going down very fast, which means that energy cost. And you can really see it in this curve here. Look how the curve just takes off here in the last 5 years on the red here. So even though we're getting improvements in density, we're actually seeing that power effect. And who would have guessed that we would have microprocessors that slow their clock down or turn a core off to prevent themselves from burning up? If you had told me that 15 years ago, I'd be crazy, it's never going to happen. But of course, it has happened. Energy efficiency has become more and more crucial, certainly for the reason that we carry around so many things. And as we move to an environment, the environment we're moving to with IoT and more intelligent devices is that they're always on. Your phone is always on. It's going to be there doing things for you, helping you out. IoT, the same thing. You want devices that are always on. So power becomes and energy becomes an increasingly crucial thing. What many people don't realize is that power is a big concern even for the people building the biggest clouds. These are numbers based on a Google Cloud, on a Google cluster installation. And they show you, we all know the most expensive thing, of course, is the computing equipment here in green. But the second most expensive thing is the power and cooling infrastructure. And even when you amortize the cost, servers get replaced roughly every 3 years, so they have a shorter lifespan. But remember, in energy cost, you also have to pay for the fuel you use to cool those machines and power them. So energy becomes a key factor, and optimizing that energy and that efficiency becomes crucial in these large clusters. So the end of Dennard scaling, for that reason, really becomes a crisis. For mobile, for the IoT space, for large clouds, we really have to worry about it significantly. But why is it such a crisis? It's such a crisis because the architecture techniques we use are inherently inefficient and have become more inefficient as time has gone by. And that's the key driver. If we knew how to build computer architectures that were faster and were perfectly efficient, it wouldn't be such a crisis. But in fact, the techniques we use are inefficient. Think about instruction level parallelism. I'll show you some data on that. But that's a technique which makes the machines run faster, but at the cost of more energy, significantly more energy. Similarly, when we have multiprocessor environments, multi-core, the inefficiency that exists due to Amdahl's law, due to synchronization, due to other things, reduces the energy efficiency of the computing mechanism. And in an environment where Dennard scaling no longer holds, that hurts a lot. Even think about something we really love, caches, an almost universal idea in computing that's had lots and lots of applications. Think about what happens when I design 2 generations of processors, and in order to keep up with the processor speed, I make the cache bigger. Well, in order to reduce the miss rate of that cache and keep the memory access time short, if I want to cut the miss rate in half, I have to do a lot more than double the size of the cache. I have to increase it by a lot more than that. So there's an inefficiency there that comes back to bite me. So what about the whole instruction-level parallelism process? We've moved from pipelining the early RISC machines, for example, the MIPS machine, the Berkeley RISC machine, were both 5-stage simple pipelines. Today, a modern Intel or AMD chip is about a 15-stage pipeline, or an ARM chip. And the energy cost of that was neutralized by Dennard scaling. We also do multiple issue. So we're doing multiple instructions per clock. Let's think about that in terms of efficiency for a minute, and we can see what the issue is. How do we get more instruction-level parallelism? Well, think about a modern, deeply pipelined processor. It's doing 4 instructions per clock. It's got a pipeline of 15 deep. That means there are 60 instructions that are in flight. There are 60 instructions that I'm operating on at some given time. Well, since there's a branch about every 4 instructions, the only way I can get 60 instructions to jam in that pipeline is by guessing, predicting, speculating on the outcome of branches. That speculation, if it's correct, allows me to proceed, fill up the pipeline with useful work. Well, how good does that branch prediction have to be? Well, here are 2 examples. Suppose that we have a 15-deep pipeline. We have 4 branches in it. In order to be 94% correct, so only 6% of the time are we doing the wrong thing, we have to have a 98.7% accuracy. But suppose we have an Intel i7, modern processor, 60 instructions in flight, means you have to predict 15 branches correctly, which means you've got to predict branches 99% correctly in order to end up throwing away your work only 10% of the time. That's really hard for modern, large-scale software systems. It's really hard to get that level of prediction accuracy. And that's what really becomes a key limit in how these machines operate. So if you look at it, here's some measurements on a Core i7. This is a machine that has a theoretical throughput of 4 instructions every clock. So cycles per instruction is 1/4. And you see that none of the benchmarks get close to that. And some of them that have particularly bad memory behavior, like MCF and this one here, have substantially more. Why is memory behavior such a critical issue? Well, whenever you get a cache miss, the pipeline has to be filled with other useful things while you're waiting for that cache to come back from those very slow DRAMs that are far away. So you fill up that pipeline, but if you don't fill it up with useful work, then you end up throwing it away. And that becomes the key limit in how these machines operate. Here's another way of looking at the same dilemma. Once you speculate, that speculation is going to put instructions in the pipeline. If you guess wrong, if the hardware does not predict a branch correctly, what happens? You fill the pipeline up, you get a lot of work in there, and then you conclude you got the branch wrong. By the way, it takes 15 cycles to conclude that you got the branch wrong. You got it wrong, you throw out all that work. By the way, you throw out all that work, you waste all the energy that it took to do all that work, and you have to reset the processor, which takes additional energy. So you can see why this inefficiency creep really becomes a bottleneck when basically power is not free. And that's the key that really has driven the end of the instruction level parallelism era. If we could have solved that problem, if we could have figured out how to get over that hurdle, we would have had a good path forward. So what happened? So we moved into this multi-core era. Architects had a really great idea. They said, well, instead of us trying to find more useful work, let's make it the programmer's job to do this work. The nice thing about the instruction level parallelism era was you went out, you bought new hardware every few years, and it was twice as fast, and you didn't have to do anything. You didn't even have to recompile your code. Once you move to a multi-core era, if you want to get greater performance, then the programmer has to get actively involved in it. You've shoved the problem of finding parallelism and useful work to do from the hardware to the programmer. Of course, that works fine, provided the programmer can find useful work. The key thing to remember is that if you think of energy as roughly proportional to transistor count, which is roughly proportional to the number of active cores, you pay the price for those cores, at least if they're turned on, whether or not they do any useful work. And that's the really hard problem to overcome. And one of the interesting things I think we've seen, some people were hoping that Amdahl's law effects would go away in these very large clusters with lots of incoming parallel streams. The difficulty is it's really hard to make the problem go away because in any system there's some level of synchronization and coordination that's necessary, and that's what limits the performance. And it's useful to remember that Amdahl's law, which basically says that any large-scale parallel system is limited by the sequential portions, is quite acute. For example, if you got a 64 processor machine and only 1% of the work is serial, so 99% of the work is parallel, a 64 processor machine gives you a speed up of about 36. So you've paid for 64 cores, you're paying the energy cost for 64 cores, and you get performance of 36. So obviously that power inefficiency, that energy inefficiency becomes a real problem. And as Moore's law begins to slow down, it adds to that because now those transistors are not nearly as inexpensive as they used to be. What about issues of thermal power as well? Well, in some cases, thermal power is probably not a big issue in large clusters. I suspect we can afford to do some exotic cooling techniques, but I don't foresee a day where I'm going to be walking around with a device in my pocket that is liquid cooled. I doubt it. Nor am I going to have that in an IoT environment where I have lots of battery-powered devices, right? So energy consumption, power dissipation becomes a big issue. If we project out what future technologies might look like in the next few years, it'll probably be possible to build a 96-core processor, and it'll have roughly a clock rate of 5 gigahertz. If you do a computation, that has an expected power consumption of 295 watts. That's certainly not something that you're going to carry around. It's even in a large data center, that's a lot of heat to get out of the processor environment. If you then make some assumptions about how many cores can be active given whatever power limit you like, say 165 watts, 180 or 200 watts, that tells you on average you can have 54, 59, or 65 of those 96 cores active. Not all 96, but some fraction of them active at any given time. If you think about what that means that the Amdahl's law effects are going to be even further exaggerated by that, because even when the application is fully parallel, you're not going to be able to get all the performance out of it. So if you look at what that means, what it does is it creates a roof line in the performance, and even with something on the order of 100 cores, 96 actually we were looking at, you can get only a fraction of the speed up that you should be able to get. Because here, instead of being limited just by, you are limited by Amdahl's law effects, but you're also limited by the number of cores you're going to have active at any given time. So some improvements, some exotic new packaging technologies that were also really cheap and suitable for carrying around in my pocket, even if I have to put a backpack with a radiator on my back, would be useful. So what opportunities are left then? This is a pretty grim story if you look at it and you look at the really tough issues we face. Grim stories always, in my mind, provide new opportunities to rethink old problems and think about them differently. And that's exactly the situation I think that exists here. We could think more about software. One of the things I observed at a conference of computer architects was the architects have been carrying the software people for a long time. It's time for the software people to carry the architects and the designers for a while. That went over very well at a computer architecture conference, as you can guess. But more about software. I mean, and I'll show you what I mean by this. In particular, if you think about what's happened with hardware and the incredible advances we've had in semiconductor technology, computer architecture, we've liberated the software people to use much more powerful programming paradigms because that was the bottleneck. The bottleneck was how quickly we could create software. So we threw lots of energy at making software run faster. That encouraged reuse. Programmers can get a lot more work done than they used to be able to do, but it comes at a significant inefficiency, and I'll show you some data on that. Efficient for programmers, but not for execution. What about hardware-centric approaches? The only path I see left is to move towards domain-specific architectures, sometimes called accelerators, things that particularly focus on one problem domain with the intention of getting much more efficiency in that problem domain. In other words, rather than try to do everything in a general-purpose fashion, we target a few particular tasks, a few kinds of applications that we can accelerate dramatically. And some combination of both hardware and software techniques as well. If we're going to have architectures that are domain-specific, we're going to have languages that are targeted at those architectures that enable us to get efficiency on those particular kinds of applications. So let's look at the software opportunity. This is from a paper coming out of MIT by Charles Licensson and a group of his colleagues. And they took a very simple example, matrix multiply. Admittedly, it's a small piece of code. It's very well structured. But they just asked the question of how much faster could that application run if it were highly optimized versus being written in Python, the #1 choice for programmers these days, writing a lot of software. So just going from writing it in Python to writing it in C increases the performance by 47 times. Okay, now, who knows a compiler that can speed up programs by 47 times? You'd be a hero if you wrote something speed up by 47 times. Well, there's a gigantic opportunity gap. If you then take that version of C and you write it with parallel loops, so you make use of a multi-core processor, you get about another factor of 9 or so from that. If you then take it and lay out the memory properly so that the caches and the memory allocation works properly, you get about another factor of 20 from that. And then if you actually use the inherent SIMD instructions in an Intel architecture, you get about another factor of 10 from that. So in the end, this version of matrix multiply runs 62,000 times faster than the naive Python-based version. Admittedly, a small example, but it shows how much inefficiency is in the system, how much efficiency we've given up in order to make the code run faster. Figuring out how to get even a fraction of that, 63,000 times, would make you a hero. So if you want to win a Turing Award, solve that problem, and I guarantee you'll get one. Okay, so Oh, that's just putting the numbers on there. So, okay, so what about hardware approaches? I think on hardware approaches, the idea that's really kicking around and has acquired some significant traction is this concept of domain-specific architectures. We achieve higher efficiency by tailoring the architecture to a particular class of domains. Not just one application. I'm not talking about a piece of hardware that's an ASIC that's not programmable. I'm talking about a piece of hardware that's programmable, but targeted at a particular domain. That requires us to think differently about how we do the design. We've got good examples of this, neural network processors for machine learning, GPUs for graphics, virtual reality. The good news is that there's lots of performance domain in these particular, lots of performance requirements and demands in this area. So, if you know anything about the work that Dave Patterson and I did in writing our books, you know that we like quantitative explanations of things. So why does a domain-specific architecture, why could it be faster? No hand-waving, let's actually try to figure out what the key concepts are. Well, the first is it makes more effective use of parallelism for a specific domain. In other words, we can move from, for example, MIMD, a multi-core design, to SIMD, single instruction, multiple data. SIMD architectures are inherently more efficient. They have to fetch one instruction stream rather than multiple instruction streams. The fact that the cores are more tightly synchronized means it's easier and more efficient to exchange information. They're inherently more efficient. But of course, I've given up something. They're less flexible. That's why the domain-specific criteria is a key one. You're thinking about a particular domain where you know more about the structure of the application than you do if you're handed a random piece of C code or Python code to run. They can also take advantage of VLIW versus speculative out-of-order techniques. The speculative out-of-order techniques are terrific if you're given a random piece of code, but they're less efficient than the VLIW techniques. VLIW is a great technology if you know enough about the application to match up the application characteristics together against the hardware limitations that exist in the VLIW. Remember, people have tried to build general-purpose VLIW machines and not been successful. Intel spent a lot of money trying to figure out how to make that work. But in the particular domain that's more limited, GPUs, for example, they work quite well. Second, we can get more effective use of memory bandwidth. Caches are a great invention, except when they don't work well. And they don't work well when we have lots of streaming data, when we have little reuse over things. In such cases, user-controlled memory hierarchies can work better. The trade-off? The trade-off is now I need enough information to control the movement of data between memories in order to make it efficient. And I've got to derive that information somehow. And in a domain-specific environment, that's probably possible. In a general-purpose environment, it's proved quite hard to do that. Third, we eliminate unneeded accuracy. Lots of applications don't need IEEE floating point in either 32 or 64-bit. They may not even need 64-bit integers or 32-bit integers. They may be able to get away with precision of 8 to 16 bits. And lastly, we need a programming model that matches between the architecture and the application. So the programming environment has to be different. We're not going to be able to get performance from these particular architectures if we assume that you're given random pieces of general-purpose code. Too hard a compilation problem. You require, if we say, okay, here's a piece of Python or C, extract the information you need to run it on a VLIW machine with user-controlled memories as opposed to caches, with SIMD structure, that problem is just too hard. I used to be a compiler researcher. I spent a lot of time trying to find and fix one part of that problem. It's just really, really hard. So we need to change the programming model. OpenCL, TensorFlow, P4 for programming network interfaces, things that have structures that are appropriate both for the domain, but also for matching to the underlying hardware. By the way, that also creates interesting new compiler challenges. One of the challenges we have in this environment is we need programs which are written in a domain-specific language, but which have enough machine independence that they can move to a slightly different domain-specific architecture and be compiled for that. If we end up in an environment where we're writing code that only runs on one peculiar processor, then we'll have lost a lot of efficiency on our programming side, and that won't work well either. So one area that's attracted a lot of attention is deep learning. And one of the reasons it has attracted attention is that the number of papers being published in deep learning is going up faster than Moore's law. That's absolutely stunning. One of the ways to think about the whole machine learning revolution, which I really like, is an example that we had at Google. They rebuilt the machine translation for doing language translation. The old version had 500,000 lines of code in, and that's without all the data for particular languages. That's just the core of it. The new version, which is based on machine learning, and of course uses lots and lots of data to program and to train, has 5,000 lines of code in it. So the amount of code's dropped by 100 to 1. A way to think about this revolution is you've taken data analysis and learning techniques, and you've used them to replace programming code that took programmers years and years to write. And that generates a lot of enthusiasm. You're actually, in the training process also, you've swapped lots and lots of machine cycles for lots and lots of programmer brain cycles. And computers are pretty cheap, so that's a good trade-off. So what are some of the research opportunities? I think one of the ones that we touched on in the PCAST report was domain-specific architectures targeted not just at the obvious things. Deep learning is one obvious thing. There's lots of interest in industry on deep learning, but also at other important computational problems and problems that are important for national security. For example, computational chemistry. Critical area, critically important problem, could have lots of implications for drug design over time, but one that probably won't get as much attention as deep learning applied to other kinds of user interface applications. So there are lots of opportunities there that we think are particularly important. There is a lot of interest around using deep learning for improving cybersecurity so that you can analyze and better understand cyber attacks based on data. And that's obviously an important area, both from a national security viewpoint as well as from a commercial viewpoint. Another area which I think is particularly important is the coevolution of domain-specific languages and domain-specific architectures. In other words, move them forward together so that they work together well. What does that mean in terms of rethinking how we design machines? This is a bit of deja vu. If you think about one of the key insights that drove the RISC revolution, the key insight was that people were not going to write a lot of code in assembly language anymore. They were going to use compilers. And what mattered was targeting the output of a compiler. I'm a child of when the Valley was a very young place. I still remember the early microprocessor wars, where Intel would come out with a microprocessor, then Zilog would come out with a microprocessor which had 4 additional new instructions in, with hand-coded examples of how those instructions could be used. No compiler in the world would ever generate those instructions. But if you were going to program everything in assembly language, which we did at one point, they were very useful. But there was a paradigm shift. We shifted to high-level languages. We shifted to Unix as an operating system rather than an operating system written in assembly language, and that changed the set of trade-offs. Similar kinds of thing happens here, where you think about domain-specific languages and domain-specific architectures mapping together, getting portability and efficiency at the same time. So, a couple of other important research opportunities, several of which we mentioned in the PCAST report. First of all, cheaper, faster hardware development. One thing is for sure, if rather than have a general purpose processor that does everything, we have a bunch of more domain-specific processors that do various tasks, we've got to get the design cost of those domain-specific processors down significantly. We need a comparable breakthrough in design cost to the one that we had in the 80s and 90s, where we made giant strides forward in our ability to design semiconductors, design integrated circuits efficiently. We need a similar thing here. Imagine a day where hardware development looks a lot more like software development, not in terms of the number of bugs they introduce, but in terms of the time to do the design, right? Hardware designers are held to a higher standard, and it's a standard that's very high. You know, recently when the meltdown inspector holes became visible, I realized that I had worked on machines, as had many other people, which had embedded a security flaw in 15 years before we discovered it. But hardware gets held to a standard to get that right and fix it, and of course it's harder to fix than software because you can't just necessarily do a new release. So we still need high levels of verification and security in our hardware, but I think we do a lot more to make hardware development more like software. More prototyping, reuse, better use of abstraction, so that things can be more easily put together and plugged together. It is a more complicated world. I wouldn't tell you that it's as equally as easy in the hardware world as the software world to build that kind of environment. It's a bigger challenge. You've got not only performance issues, you've got area, cost, power, you've got more things you have to worry about than we have to worry about in the software world. But I think it's critical to really be able to do a better job on issues like reuse and abstraction. We need new CAD tools. I think we're reaching the level of capability for our current CAD tools. We need people to rethink how we do CAD and how we do synthesis even better than we do. We need open hardware stacks. It should be just as easy to go out and get a piece of hardware and get it interfaced as it is for current software environments. We need fast prototyping techniques. FPGAs are one of the great ways in which this has happened. Other ways to build fast chips, iterate quickly, cut down the design cycle so that we can get chips out faster. And I think there are interesting questions of what role machine learning might play in the whole CAD environment. Could we unleash machine learning techniques to give us more effective design ability, trading lots of compute power for the shortage of design cycles that we otherwise have? I think we also have to think seriously about new technology. Silicon is obviously reaching the end of it. If you figure out a way to extend silicon, get Moore's Law 2, overcome the Dennard scaling problem, that would be terrific. Those are really hard problems, though. New methods for efficient energy scaling are going to be critical. I think also we need to think about things like secure supply chains, one of the issues we mentioned in PCAST. That becomes an increasingly important issue. Packaging. If you can afford to get the heat out and put it somewhere else, that gives you a great deal of flexibility in terms of building additional processors. Some of you may have seen that the next generation TensorFlow processing unit from Google is going to use liquid cooling. That's clearly appropriate for a data center, but it's not appropriate for lots of other applications. Tighter integration. Obviously, the more things we can get packaged close together, whether through some die stacking techniques or other techniques, the better off we'll be. What about integrating 3.5s for optical interconnects so we could reduce interconnect overhead? If you could integrate them sufficiently, you might overcome the power disadvantages that come from switching from silicon to a 3.5 in order to do interconnect. And of course, beyond silicon, whether it's carbon nanotubes or quantum. I don't know what the technology beyond silicon is. What I notice is that most of the people working on these are physicists as opposed to engineers. And I always think when a physicist is working on it, it's 10 or 15 years before the engineers get their hands on it and start using it. So we've got to continue that work because we've got to figure out what follows on. So just a few concluding thoughts. Dave Cook, who worked on a famous machine, the Iliac 4, circa 1975, he was, by the way, when they built the Iliac 4, they had one software architect. He was the software architect. And of course, what happened in the Iliac 4 was they built an incredible piece of hardware, but nobody could figure out how to use it. The key idea, we've got to be able to match together the hardware we build together with the languages and software that uses them. I think this is a critical time because information technology has become more important in our lives than ever before. And it's a critical investment for the country. We rely deeply on information technology and the semiconductor technology that underlies it. It's critical to the economic and security asset for any nation. Figuring out how we continue to lead as we have for the last 40 years is really going to be a critical problem, and it's going to require the best young minds in the country to work on it. So I'm delighted that DARPA is investing in ERI because I think it's crucial for our future, and it's crucial for all of us who've had the opportunity to work in this industry to continue to see it flourish. Thank you for your attention, and thanks for coming to this terrific meeting.
Thank you so much.
Thanks, Bill.
All right, so thank you on so many different levels, specifically to remind us all that because if you get to upper management, you don't lose your fastball. So, all right, so a couple of questions. You know, you led the PCAS team, and you had some really insightful discussions about what we should be doing. Can you highlight what you think the most critical thing is for the country that the PCAS report identified?
I think the most important recommendation was run faster is the only way forward. You've got to run faster, you've got to reinvent yourself. You know, when we started, we had a long discussion about an earlier time in the industry when we thought the industry was going to be somewhere on the Pacific Rim and not in the US anymore. And we were all concerned about that. And how did we get back ahead? We reinvented the future, right? And that's what I think we need to do here. So you've got to run faster. Trade barriers, good trade relations are a good thing, but trade barriers may not be the answer to everything. You've got to figure out how to stay in the lead and create the future.
Well, thank you so much.
Okay,
it's been
thank you.
Very instructive.